In this series of films on optical systems, this is the first film on optical detectors. And let's first look at proximity detectors, detectors that detect if there is an object in the path or if there's not an object in the path. We have three different ones. We have through beam, diffuse reflective, and retro reflective. Through beam is when the object breaks the line between the transmitter and the receiver. TX transmitter, RX receiver. So the object here shadows for the light so it doesn't reach the receiver. That requires power supply on both ends, and that also but it's quite safe since you actually break the line here. Diffuse reflective means that the object itself is what reflects the light back to the receiver, while retro reflective means that you have a reflector or some kind of a mirror here and back to the receiver there, and the object breaks the line between the two. This is where you find in gate openers at food stores, etc. The source is a LED, or maybe it's also sometimes visible, sometimes ultraviolet, or it may even be a hot object. The receiver is a phototransistor, photodiode, or photoresistor. In most cases, a phototransistor. Modulated light is sometimes used to separate the light from the transceiver from the light in the surroundings. So if you, for example, use some kind of blinking that the receiver recognizes, that means that it's the light from the transmitter, not from the ambient sources in the shop or wherever. Encoders are used to count the rotations of a disk. Of course, this disk can roll along a board or something, which means that it can measure distance. You have two kinds. You have absolute rotary encoders and you have incremental rotary encoders. The absolute have different sectors in the disk here, so you can detect at which point on the disk you are, while the incremental only have slots. So these are simpler. These are more advanced. The simpler ones here are basically used to count or to find the rotational speed of the axis, while this one is used to find the specific position of the axis. And if you imagine that you roll this wheel along a board, you can actually find out how long it has rolled. And you can find out also in which direction it rolls. You can't find that out here. Displacement of fiber means that you have three ways actually of detecting the displacement of a fiber. You can move the fiber in this case in the horizontal plane, which means that the gap increases, which means that the amount of light that escapes from the source here in the gap will increase when you make the gap larger. Transverse means that you shift the fiber up and down in this case, and of course the amount of light that escapes from the gap here will increase when the distance increases. The same with angular. The higher the angle, the more light escapes due to that you're out of the region of total internal reflection. In some cases you will find differential fibers, which means that you have two, so you can see in which direction you are moving the fiber. In this transverse example, you can only see that it's taken out of the straight line relation between the two, while this one you can see in which direction it has shifted. These kind of displacement fiber sensors are used in areas where you cannot have electronics, so in hazardous areas and so on. You can also use light here, for example, you have a sender and a detector, and you have a reflective patch on an axis, for example, on a shaft, and when this rotates, this one counts the pulses from the reflection, which means that it detects the rotations per minute or per second. Here, an example of a level meter, multiple detectors. Here is an example of a displacement sensor where you have a reflective surface. Light is sent to a fiber and back up here. Here, an angular detector. The higher the angle, the more light goes. Most of the light goes in here and less in here from the source. Actually, you have a graph like this because if the sender and detector are too close to each other, very little light will transfer from the sender to the detector. And then you have a perfect distance between the source and the detector where much light goes through, and then if the separation becomes too high, again too much light escapes. So by having two detectors and one sender, you can determine at which point you are here on this full graph. For example, you can use this as a part of a pressure sensor, where this is the membrane between two chambers. Other examples, level detector. This is actually level switch. When this prism here is soaked in a liquid, the refractive index difference between the prism and the liquid is not high enough to achieve total internal reflection, so some of the light will escape into the liquid, and therefore the amount of light that is sent up to the detector is reduced. Here, oil in water detector. If you have an open piece of fiber without cladding, if droplets form here, you will have light escaping because the change in diffractive index from glass to oil is lower than the one from glass to air, in this case, or glass to water. Microbends. If you have two sections like this that bends the fiber between them, of course you cannot bend the fiber so much that it will actually crack. So it only allows for quite small bends, but still. But if you push this upper bar towards the lower, you will have more intense bendings, which means that more light will escape from the core of the fiber.